So Newton's law of universal gravitation basically says that every object in the universe attracts every other object. And the force between those objects is directed between the centers of the objects. So when we measure the distance between them, see we've got it here marked with a D, notice that it's measuring from the center of each of these objects here. And Newton was able to figure out that the gravitational force is directly proportional to the product of the object's masses. Remember, product means that you multiply things together. So when you multiply the masses together, okay, mass 1 times mass 2, if that goes up, then the force is going to go up. If the masses goes down, or if the product between masses goes down, then the force is going to go down. And I do want to point out over here where it says F1 equals F2. Remember Newton's third law of motion. For every action, there's an equal and opposite reaction. So if this planet or this object is pulling on the other one with this much force, then the second one is pulling with exactly the same amount of force. Okay, so the forces are equal. Newton also figured out that the force was inversely proportional to the square of the distance between the objects. Okay, remember inversely proportional means if one goes up, the other one goes down. And this is a special kind of proportion because we have to square the distance. So it's not just if it is doubled, then one goes down by half, but it's a little bit more complicated than that, which I will show you in just a moment. So we know that gravitational force between objects increases when the mass increases. So if I were to multiply one of my masses by 2, that would multiply my force by 2. Okay, if I do it to one side, I have to do it to the other side. But what if I multiply both masses by 2? Well, now I'm multiplying 2 times 2. So that's going to make my force 4 times higher. Now we also know that gravitational force decreases as objects get farther apart. Now here's where it can get a little bit tricky. So let's say that I take my two objects and I double the distance between them. Okay, now they're twice as far apart. So it looks like I'm dividing by 2. But I'm not just dividing by 2. I'm dividing by 2 squared. So I have to do the same thing to the other side of my equation, and I have to divide that by 2 squared, which is 4. So if I double my distance, my force goes down by 1/4. We can also go the other way and show how the force would increase. If my objects get closer together, let's say, let's say that I cut my distance in half. Now they're closer together than they were before. And again, I'm not just cutting it in half, cutting it in 1/2 squared. Well, that's dividing by 1/4. And as we know, when you divide by a small number, your one gets bigger. So if I divide by 1/4, my force will become 4 times stronger. Okay? So just remember that force and distance do the opposite of each other. So if distance goes down, force goes up. If distance goes up, force goes down. Now we come to this guy named Henry Cavendish. And Henry Cavendish, in 1798, performed this experiment. He wanted to weigh the Earth. He wanted to know how much mass was in the Earth. And in doing so, in this experiment, what he also discovered is what's called the gravitational constant. Now, Newton knew that all of these things were proportional, that the gravitational force was proportional to the product of objects' masses and to the distance between their centers. But he couldn't quite figure out, it was never equal to that. There was always a piece missing. And Henry Cavendish performed this experiment and he found that missing piece. The gravitational constant is the magnitude of force exerted by two 1 kilogram masses placed 1 meter apart. And what that means is that this is sort of the ratio for every object in the universe. And this G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. It's this big, long number. That's a constant everywhere in the universe, and that ratio holds true every single place in the universe. So this G, this big G right here, we're going to use in every single calculation of gravitational force. But be really, really careful of the difference. Remember, I've talked about the difference between capital letters and lowercase letters, and be really careful when you're using one or the other, because sometimes we'll use them both. Well, this is one of those cases. So little g, a lowercase g, is acceleration due to gravity. Okay, remember the lowercase is acceleration. Big G, the capital G, is a constant, and that's a number that's going to be placed into every single calculation that we do with the new equation that is coming up. So here's the final equation. Between Newton and Cavendish, we came up with this. And so we know that gravitational force, which is measured in newtons, is equal to G, okay, and G is a constant, times both object masses, so G times mass. It doesn't matter which one is mass 1 and mass 2, as long as you know which is which, divided by the distance squared, distance between the object centers. And this squared is really, really important. It's going to make a big difference in your calculations. So be very careful that you always square your distance. We can rearrange that equation also to solve for other variables. Let's say that you want to know the mass of one object and you have all the other pieces. So mass is equal to the force, the gravitational force, times distance squared, divided by big G, that constant, times the other mass. And then you can also solve for the distance between objects. And that's going to be the square root of G times both masses divided by your force. And this is another case where you have to be really careful to square root, otherwise that's going to affect your answers.